Imagine this. Our fastest spacecraft is racing away from Earth at 38,000 miles per hour. At this speed, you could circle our planet in 40 minutes. You could reach the moon in 10 hours. You could travel from New York to Los Angeles in 4 minutes flat. This is the pinnacle of human propulsion technology, the greatest velocity we have ever achieved with a manufactured object. And at this speed, reaching our nearest neighboring star would take over 70,000 years. That is longer than modern humans have existed, longer than we have had language, art, or fire. Every human being who has ever lived, every civilization that has risen and fallen, every empire that conquered and crumbled, all of it would fit within the time needed to reach just one nearby star. Scientists have run the numbers on every proposed technology, from nuclear pulse engines to antimatter drives. The conclusion is devastating. The stars may be forever beyond our reach. If you want to understand why humanity might be permanently trapped in our solar system, please like and subscribe. Now, settle down and make yourself comfortable. Let's begin. Look up at the night sky on any clear evening. Those pinpricks of light appear close enough to touch, close enough that ancient humans imagined walking among them after death. The stars seem to form a canopy just beyond the clouds, a ceiling decorated with luminous jewels waiting for visitors. Children reach toward them with outstretched hands, believing they might grasp one if only they could climb high enough. This optical illusion represents one of the cruelest tricks the universe plays on conscious beings. Those stars are not close. They are not waiting for visitors. They exist at distances so vast that the human brain literally cannot process them without resorting to mathematical abstraction. Every culture throughout history has projected meaning onto the stars. The ancient Greeks saw heroes and monsters traced in stellar patterns. The Egyptians aligned their pyramids with celestial bodies they believed housed the souls of pharaohs. Indigenous peoples across every continent developed creation myths, explaining how the stars came to be and what they represented. All of these stories share one fundamental assumption: the stars exist within reach of human significance, close enough that our actions and beliefs might matter to them. Modern astronomy has shattered this comforting illusion, while replacing it with something far more magnificent and far more terrifying. The stars are not decorations hung for our benefit. They are other suns, nuclear furnaces burning with the same fires that warm our planet, scattered across distances that make human experience irrelevant. The nearest star to our sun is Proxima Centauri, a dim red dwarf lurking 4.24 light-years away. This measurement sounds almost manageable when expressed in astronomical shorthand. 4 light-years, a small number, something a spacecraft might traverse given enough time and determination. Astronomers toss around these figures casually, discussing stellar distances as though they were merely large rather than incomprehensible. Confirmed measurements reveal what this distance actually means. A light-year represents the distance light travels in 1 year, moving at 186,000 miles per second. Write that number out. 186,000 miles every single second. Light circumnavigates Earth 7 times in the duration of a single heartbeat. In the time it takes you to blink, light has travelled from New York to Los Angeles and back roughly 25 times. A beam of light leaving the sun reaches Earth in 8 minutes, passes Mars in roughly 12 minutes, crosses the orbit of Jupiter in about 43 minutes, and reaches Saturn in approximately 79 minutes. Within a few hours, that same beam of light exits our entire solar system, passing beyond the orbit of Neptune and continuing outward into the interstellar void. Nothing can exceed it. Nothing can even approach it without requiring infinite energy. Albert Einstein proved this over a century ago, and every experiment conducted since has confirmed his equations with devastating precision. 4 light-years means that light itself, travelling at the absolute cosmic speed limit, requires 4 years and 3 months to bridge the gap between our sun and its nearest neighbour. Think about what has happened in your life over the past 4 years. Relationships have begun and ended. Jobs have changed. Children have grown. People you loved have died. Governments have risen and fallen. All of human activity during that span represents the time needed for light, the fastest thing in existence, to reach merely the closest star. The photons leaving Proxima Centauri tonight began their journey when you were making different decisions, living a different life, perhaps not even born yet depending on your age. By the time those photons reach your eyes, years of your existence will have passed. You are not seeing that star as it exists now. You are seeing its past preserved in ancient light that has travelled across emptiness you cannot imagine. Every star in the night sky shows you history, not present reality. Now, consider what this means for physical objects. The Voyager 1 spacecraft, launched in 1977, represents humanity's fastest interstellar traveller. This nuclear-powered probe has been accelerating away from Earth for nearly 5 decades, using gravitational assists from Jupiter and Saturn to achieve speeds no other human-made object has matched. Engineers designed Voyager to explore the outer planets, never imagining it would become our first emissary to interstellar space. Voyager 1 currently travels at approximately 38,000 miles per hour relative to our Sun. At this velocity, Voyager 1 covers roughly 1 million miles every single day. 1 million miles. The distance from Earth to the Moon is only about 240,000 miles. Voyager travels more than 4 times the Earth-Moon distance every 24 hours. This sounds impressive until you calculate how long the journey to Proxima Centauri would require. The distance to our nearest stellar neighbour measures approximately 25 trillion miles. Written out completely, that number spans 13 digits. 25 followed by 12 zeros. At Voyager speeds, crossing this gulf would take 73,000 years. 73,000 years. Let that number settle into your understanding. Truly let it penetrate your assumptions about what space travel means. When Voyager 1 reaches the distance of Proxima Centauri, assuming it was heading in that direction which it is not, the year will be approximately 75,000 CE. No human being can conceptualize 73,000 years of continuous travel. Our minds evolved to plan hunting expeditions and seasonal migrations, not voyages spanning geological epochs. Human beings first developed behavioral modernity around 50,000 years ago. This means our ancestors began creating art, developing complex language, and engaging in symbolic thought roughly 50 millennia in the past. Everything that makes us distinctly human. Every painting on cave walls, every story told around ancient fires, every tool crafted with intention and foresight, all of it emerged within a time span shorter than the journey to one nearby star. Agriculture emerged only 12,000 years ago in the Fertile Crescent. The entire history of farming, of settled civilizations, of cities and empires and written records fits comfortably within 1/6 of the time needed for our fastest spacecraft to reach Proxima Centauri. Writing was invented approximately 5,000 years ago. The Sumerians pressed wedge-shaped marks into clay tablets, creating the first permanent records of human thought. Every historical figure you have ever learned about lived after this development. Every empire and religion and scientific discovery that left written evidence of its existence occurred within the past 5 millennia. All of recorded human history represents less than 7% of the voyage time to one nearby star. Cleopatra ruled Egypt closer to our present time than to the construction of the Great Pyramids. This fact often surprises people because we mentally compress ancient history into a single, distant era, but the pyramids stood for over 2,000 years before Cleopatra was born. The entire span from Cleopatra to now, encompassing the Roman Empire, the Middle Ages, the Renaissance, the Industrial Revolution, both world wars, and the Space Age, still represents only about 3% of the journey time to Proxima Centauri. If ancient Egyptians had launched a Voyager-class spacecraft toward our nearest stellar neighbour at the moment they laid the first pyramid stones, that craft would still be less than 1/15 of the way there today. It would have approximately 68,000 years of travel remaining. The spacecraft would arrive at its destination so far in the future that human civilization as we know it would be unrecognizable if it still existed at all. But the reality is actually worse than this calculation suggests. Voyager 1 is not heading toward Proxima Centauri. Its trajectory carries it in a completely different direction through interstellar space. The probe will pass within 1.6 light-years of a different star called Gliese 445 in approximately 40,000 years. Even this close approach represents a vast cosmic distance, more than 9 trillion miles, and Voyager will simply drift past without stopping. By the time Voyager reaches even this relatively close stellar encounter, it will be a dead hunk of metal tumbling through the void. Its power supply will have been exhausted for tens of thousands of years. Its instruments will be silent. Its computers will be frozen. Its golden record, carrying greetings from a civilization that may no longer exist, will spin forever in the darkness, waiting for alien ears that may never hear it. The plutonium that powers Voyager decays continuously according to predictable physics. The radioisotope thermoelectric generators that convert this decay into electricity produce less power each year. By 2030, insufficient energy will remain to operate any scientific instruments. The spacecraft will continue outward, propelled by momentum alone, but it will be blind and deaf and mute. If alien beings someday intercept our interstellar message in a bottle, they will find only a technological fossil from a species that perished or evolved beyond recognition during the probe's endless journey. The cruel mathematics of interstellar distance scale upward from Proxima Centauri with terrifying consistency. Sirius, the brightest star in our night sky, lies 8.6 light-years distant. This brilliant beacon has guided sailors and inspired mythologies for thousands of years. Ancient Egyptians based their calendar partly on its heliacal rising, yet at Voyager speeds, reaching Sirius would require approximately 170,000 years. 170,000 years ago, anatomically modern humans had just begun migrating out of Africa. Neanderthals still dominated Europe. Multiple human species coexisted across the planet. The journey to Sirius would require the entire span from that prehistoric exodus to the present day, and then nearly that same span again into the future. Vega, the brilliant blue-white star visible directly overhead during summer evenings in the northern hemisphere, sits 25 light-years away. This star once served as Earth's North Star roughly 14,000 years ago, and will do so again in about 12,000 years due to axial precession. Reaching Vega at Voyager speeds would demand a voyage of nearly 500,000 years. 500,000 years ago, Homo heidelbergensis walked the Earth, an ancestor species that would eventually give rise to both modern humans and Neanderthals. The journey to Vega would span the entire evolutionary history from that ancestral species to us, and then continue for twice that duration into an unimaginable future. These timescales exceed not just human civilization but human existence as a species. Homo sapiens emerged approximately 300,000 years ago in Africa. The journey to Vega at our current best speed would require nearly twice the entire duration of our species' existence. You would need to launch a spacecraft before modern humans evolved, and wait for it to arrive after we have potentially evolved into something else entirely or gone extinct. Consider Betelgeuse, the red supergiant marking Orion's shoulder. This dying star captivates astronomers because it may explode as a supernova within the next 100,000 years, potentially becoming visible during daylight from Earth. Betelgeuse sits approximately 700 light-years from our solar system. At Voyager speeds, reaching this stellar giant would require 14 million years. 14 million years ago, Great apes were just beginning to diverge into the lineages that would eventually produce humans, chimpanzees, and gorillas. The dinosaurs would have needed to launch that mission while they still roamed the Earth. And their distant descendants, whatever forms they might take after such incomprehensible evolutionary time, would be the ones to see it arrive. The stars visible to naked eyes represent merely our immediate cosmic neighborhood. They form a tiny sphere around our solar system, a bubble of accessible light containing roughly 9,000 stars within a radius of about 300 light-years. This seems like a substantial number, until you realize it represents approximately 0.000004% of the stars in our galaxy. The naked eye sky shows us our cosmic backyard, not the universe. Yet even the closest of these visible neighbors exists at distances requiring tens of thousands of years to traverse with current technology. Every star you can see without a telescope lies forever beyond reach of any spacecraft humanity has ever built. The night sky creates an illusion of proximity that mocks our technological capabilities. Beyond this immediate neighborhood stretches our galaxy, the Milky Way, containing between 200 billion and 400 billion stars spread across 100,000 light-years. The sheer number overwhelms comprehension. If you could count one star per second without stopping to sleep or eat, completing a census of just the low estimate would require over 6,000 years. The high estimate would take nearly 13,000 years of continuous counting. At Voyager speeds, crossing our own galaxy would require approximately 2 billion years. The Sun would have exhausted its hydrogen fuel and expanded into a red giant, consuming Earth long before any spacecraft launched today could traverse galactic distances. Our planet would have been vaporized, our solar system transformed beyond recognition. While the probe was still less than halfway across the Milky Way, this is the first terrible truth about interstellar travel. The speed of light is both the universe's absolute speed limit and a velocity so inadequate for cosmic distances that it mocks our aspirations. Light itself requires 100,000 years to cross our galaxy. Nothing can travel faster. Nothing can even approach that speed without requiring infinite energy, and even light speed proves pathetically slow against astronomical scales. Scientists express interstellar distances using a unit called the parsec, equivalent to 3.26 light-years. This measurement derives from parallax observations, the apparent shift in stellar positions as Earth orbits the Sun. Our nearest stellar neighbor lies 1.3 parsecs away. The nearest star known to host potentially habitable planets, also Proxima Centauri, exists at this same distance. The nearest Sun-like star, Alpha Centauri A, sits slightly farther at 4.37 light-years. Proxima Centauri does host a planet in its habitable zone. Discovered in 2016, Proxima Centauri B orbits at a distance where liquid water could theoretically exist on its surface. This world has captured scientific imagination as a potential destination for future interstellar exploration. The planet may have a mass similar to Earth's. It may have an atmosphere. It may harbour conditions compatible with life as we understand it. Yet this tantalizing target, the closest potentially habitable world to Earth, might as well exist in another universe given current propulsion technology. 25 trillion miles of emptiness separate us from a world that may be remarkably similar to our own. We can study it with telescopes. We can analyze the light passing through its atmosphere. We can speculate endlessly about what might exist on its surface. But we cannot visit it. Not in our lifetimes. Not in our children's lifetimes. Possibly not ever. These distances create a fundamental barrier to exploration, unlike any humanity has previously faced. When European explorers crossed the Atlantic, they faced journeys of weeks or months. Dangerous, certainly, but survivable. When they ran low on supplies, they could stop at islands. When storms damaged their ships, they could make repairs using materials found along the way. The ocean, for all its dangers, contained resources that travellers could exploit. Unlike oceanic voyages, where ships could resupply at ports and islands, Interstellar space contains nothing. No fuel depots, no rescue stations, no waypoints where travelers could rest and repair. The void between stars represents the most perfect vacuum in nature, a realm of almost absolute emptiness, where individual atoms may be separated by distances measured in miles rather than millimeters. The implications for travel become starkly clear when you consider what sustaining a voyage would require. A spacecraft traveling to Proxima Centauri would need to carry every resource required for the entire journey from the moment of launch to the moment of arrival. Every calorie of food for every crew member for every day of travel. Every breath of oxygen they would inhale. Every drop of water they would drink. Every replacement part for every system that might fail. Every joule of energy needed for course corrections, communication, and arrival maneuvers. Nothing could be obtained along the way because nothing exists along the way. There are no cosmic gas stations where a spacecraft could refuel. No supply ships could be sent to intercept a struggling mission. No rescue would be possible if systems failed. A spacecraft traveling between stars would be more isolated than any vessel in human history. Alone, in a void so empty that the concept of location itself loses meaning. The interstellar medium, the technical name for the space between stars, contains roughly 1 atom per cubic centimeter on average. This is not empty in the sense of a sealed vacuum chamber. It is empty in a way that defies human experience. For comparison, Earth's atmosphere at sea level contains approximately 27 billion atoms per cubic centimeter. The interstellar void is emptier than the best vacuum chambers humans can create in laboratories, emptier than anything we have ever experienced directly. The most advanced vacuum systems on Earth, used in particle accelerators and semiconductor manufacturing, achieve pressures where billions of molecules remain in each cubic centimeter. Interstellar space makes these sophisticated chambers look crowded by comparison. The emptiness between stars approaches the theoretical limit of nothingness, where matter becomes so sparse that a spacecraft could travel for years without encountering a single atom. This emptiness extends across distances that dwarf human comprehension. If you could somehow survive in interstellar space and look back toward the sun, our star would appear as merely another point of light, indistinguishable from thousands of other stars in the stellar background. Continue traveling outward, and the sun fades to invisibility, lost among countless other distant suns. At the halfway point between our solar system and Proxima Centauri, approximately 2.1 light-years from either star, both would appear as unremarkable points of light, offering neither guidance nor comfort. The psychological impact of this isolation may prove as insurmountable as the physical challenges. Human beings evolved in communities. We are profoundly social creatures who require connection, communication, and the presence of others to maintain mental health. Our brains develop to function within tribes of perhaps 150 individuals, surrounded by familiar landscapes and supported by social bonds stretching back generations. A spacecraft traveling between stars would exist in isolation more profound than any human has ever experienced. Antarctic researchers report significant psychological difficulties after months of winter isolation, when darkness covers the continent and evacuation becomes impossible. Submarine crews show elevated stress levels after weeks, submerged in confined quarters with limited communication. Orbiting just 250 miles above Earth's surface, with constant communication links to mission control and the psychological comfort of seeing their home planet through every window, still experience measurable psychological challenges from their relatively brief 6-month missions. Now imagine decades of travel through absolute emptiness. Imagine looking out a window and seeing nothing but the unchanging stars. The same view, day after day, year after year, decade after decade. Imagine being unable to see Earth, unable to receive timely communication from loved ones, unable to return regardless of any emergency that might arise. Imagine knowing that the people you left behind are aging and dying while you hurtle through void. that every day of travel represents months or years of time passing at home due to relativistic effects. Current propulsion technology makes interstellar travel effectively impossible within meaningful timeframes. Chemical rockets, which have launched every spacecraft humanity has ever built, achieve exhaust velocities of roughly 3 to 4 kilometers per second. This provides enough thrust to escape Earth's gravity and travel within our solar system, but falls billions of times short of what interstellar voyages would require. The space shuttle's main engines, among the most powerful chemical rockets ever built, produced exhaust velocities of approximately 4.4 kilometers per second. The mighty Saturn V rocket that carried Apollo astronauts to the moon achieved similar performance. These magnificent machines represented the absolute pinnacle of chemical propulsion technology, engineering marvels that required the resources of entire nations to develop and operate, and they could barely push humans beyond Earth's immediate neighborhood. The fastest possible chemical rocket, using the most energetic fuel combinations known to chemistry, could not exceed exhaust velocities of approximately 5 kilometers per second. This limit arises from fundamental chemistry, from the amount of energy stored in molecular bonds. At these speeds, reaching Proxima Centauri would still require tens of thousands of years. Chemistry itself imposes this ceiling. No arrangement of atoms can store more energy per kilogram than the best existing rocket fuels. Hydrogen and oxygen combustion releases energy at rates determined by the electromagnetic interactions between electrons in chemical bonds. You cannot make these bonds stronger. You cannot extract more energy from their breaking. The laws of chemistry set an absolute limit on chemical propulsion that no engineering cleverness can overcome. We have essentially reached the end of what chemical rockets can achieve. This realization has driven scientists to explore alternative propulsion concepts. Nuclear thermal rockets, ion drives, solar sails, nuclear pulse propulsion, antimatter engines, laser-powered light sails. Each technology promises improvements over chemical rockets. Each has inspired decades of research and speculation. Each faces fundamental limitations that may prove insurmountable. The mathematics of interstellar travel creates what engineers call the tyranny of the rocket equation. This formula, derived by Russian scientist Konstantin Tsiolkovsky in 1897, describes the relationship between a rocket's starting mass, ending mass, and the velocity change it can achieve. The equation appears deceptively simple. Delta V equals exhaust velocity multiplied by the natural logarithm of the ratio between initial mass and final mass. But that natural logarithm conceals an exponential monster. Accelerating to high speeds requires exponentially increasing amounts of fuel, which itself requires additional fuel to accelerate, creating a cycle that rapidly spirals toward impossible mass ratios. To double your velocity change, you do not merely need to double your fuel. You need to square your fuel to payload mass ratio. To triple velocity change, you must cube that ratio. The numbers explode toward infinity with terrifying speed. For a chemical rocket to reach even 10% of light speed, the required fuel mass would exceed the mass of the observable universe. This is not an exaggeration. This is not hyperbole designed to emphasize a point. Calculate the numbers yourself if you doubt this claim. 10% of light speed equals approximately 30,000 kilometers per second. Chemical rockets achieve exhaust velocities of perhaps 5 kilometers per second. Plug these values into the rocket equation and watch the result overflow any calculator you might use. The mass of fuel required exceeds not just Earth, not just the Sun, not just the Milky Way galaxy, but the entire observable universe containing 2 trillion galaxies. The exponential nature of the rocket equation creates absurdities that no amount of engineering can overcome. Reaching speeds necessary for practical interstellar travel demands propulsion technologies fundamentally different from anything we currently possess. We need not merely better rockets. We need entirely different approaches to acceleration that somehow circumvent or exploit loopholes in the tyranny of rocket physics. Yet even achieving 10% of light speed a velocity so far beyond current capability that it borders on science fiction even for our most optimistic projections, would reduce the journey to Proxima Centauri to only 40 years, fast enough that a crew could potentially survive the voyage, but slow enough that mission planners would need to account for aging, disease, equipment degradation, and countless other challenges over 4 decades of complete isolation, 40 years of travel through emptiness, 40 years without resupply, 40 years of life support systems that cannot be allowed to fail even once, 40 years of cosmic radiation bombarding human bodies, 40 years of psychological isolation that no human has ever endured. And this represents the optimistic scenario, the science fiction dream of achieving velocities millions of times faster than anything we can currently accomplish. The void between stars is not merely empty, it is actively hostile in ways that make Earth's harshest environment seem welcoming by comparison. Interstellar space has no temperature in the conventional sense because temperature requires matter to have temperature. Objects traveling through this void radiate their heat into nothingness, cooling toward absolute zero unless they generate their own warmth through nuclear decay or other processes. Cosmic radiation permeates every cubic meter of interstellar space. High-energy particles accelerated by supernova explosions, black hole accretion disks, and other violent cosmic events streak through the void at velocities approaching light speed. On Earth, our planet's magnetic field and thick atmosphere block or deflect most of this radiation. In interstellar space, nothing blocks anything. Every particle that approaches will arrive. The stars beckon us with their ancient light. They whisper promises of worlds beyond counting, planets where life might flourish under alien suns, mysteries waiting to be discovered across cosmic distances. We have now detected more than 5,000 exoplanets orbiting other stars. Some orbit within habitable zones where liquid water could exist. Some show atmospheric signatures suggesting the presence of water vapor or other potentially life-supporting compounds. Some may harbor civilizations that gaze back at our sun and wonder if anyone lives here. But between us and those distant lights lies an ocean of emptiness so vast that crossing it may forever exceed human capability. The prison of light contains everything we can see, yet allows us to reach almost nothing we observe. We are granted a view of infinity while being confined to a single point. Every technological advance in astronomy shows us more worlds we cannot visit. Every improvement in telescope sensitivity reveals more tantalizing targets that exist beyond any possible journey. The ancient Greeks looked at the stars and imagined heroes placed among them by grateful gods. Medieval scholars believed the stars were holes in a crystalline sphere, revealing divine light from heaven beyond. Modern humans know the stars are distant suns, many hosting planets, some potentially harboring life or even civilizations. Our knowledge has expanded enormously across the centuries. Our physical reach has not extended beyond Earth's immediate neighborhood. This is where our journey of understanding begins. With the cold, confirmed mathematics of distance and time. With the brutal reality that our fastest spacecraft would require longer than human civilization has existed to reach one nearby star. With the recognition that the stars we see each night are not destinations we might someday visit, but rather lights illuminating the walls of our cosmic prison. The universe has given us eyes to see infinity, while binding our bodies to a single mote of dust orbiting an unremarkable star in the outer suburbs of an ordinary galaxy. Every proposed method of interstellar propulsion faces the same fundamental obstacle. The energy required to accelerate mass to velocities where interstellar travel becomes practical exceeds anything humanity has ever generated. The numbers are not slightly discouraging. They are not challenging in the way that building the pyramids was challenging or landing on the moon was challenging. They are cosmically prohibitive, requiring power outputs that dwarf entire civilizations combined across all of recorded history. Engineers and physicists have spent decades analyzing every conceivable propulsion technology. They have calculated thrust-to-weight ratios, exhaust velocities, fuel consumption rates, and energy requirements for systems ranging from conventional rockets to theoretical concepts that border on science fiction. The conclusions are consistent across every analysis. The laws of physics themselves conspire against interstellar travel in ways that no amount of engineering cleverness can overcome. Consider the baseline challenge in concrete terms. Reaching Proxima Centauri within a human lifetime, say 50 years, requires average velocities of approximately 10% of light speed. This translates to roughly 30,000 kilometers per second, or 108 million kilometers per hour. These numbers sound abstract until you compare them to velocities humans have actually achieved. The International Space Station orbits Earth at roughly 28,000 kilometers per hour. This is fast enough that astronauts witness 16 sunrises and sunsets every 24 hours as they circle the planet. The station covers the distance from New York to Los Angeles in about 8 minutes. This represents one of the highest sustained velocities at which humans have ever traveled. Interstellar travel at 10% light speed requires velocities nearly 4,000 times faster than the International Space Station. If the station represents a leisurely walk, interstellar travel represents a sprint so fast that the walker would need 4,000 steps to match a single stride. The comparison breaks down because human intuition cannot grasp what 4,000 times faster actually means. Let us try another comparison. The fastest human-made object ever created was the Parker Solar Probe, which achieved velocities exceeding 400 to 30,000 miles per hour during its close approach to the Sun in 2024. This spacecraft traveled faster than any object in human history, fast enough to travel from Earth to the Moon in under 30 minutes. Yet even this record-breaking velocity represents only about 0.06% of light speed. Interstellar travel would require speeds roughly 170 times faster than the fastest thing humanity has ever built. The kinetic energy of a moving object increases with the square of its velocity. This mathematical relationship sounds innocuous until you work through its implications. Double your speed and you quadruple your energy requirement. Triple your speed and energy requirements increase ninefold. Increase speed by a factor of 10 and energy requirements increase by a factor of 100. Now consider what this means for interstellar travel. The International Space Station moves at roughly 28,000 kilometers per hour. Achieving 10% of light speed requires increasing velocity by a factor of approximately 4,000. Energy requirements, therefore, increase by a factor of 16 million. The energy needed to accelerate a spacecraft to interstellar velocities exceeds the energy needed for Earth orbit by 16 million times. This is not a problem of building bigger rockets or developing better fuels. This is a fundamental physical constraint arising from the relationship between mass, velocity, and energy. No engineering breakthrough can change the fact that kinetic energy scales with velocity squared. This law applies everywhere in the universe, to every species that might attempt to build spacecraft, regardless of their technological sophistication. Scientists have calculated the energy needed to accelerate a 1 kilogram payload to 10% of light speed. Written out, this number spans 15 digits. For context, this equals the total energy released by exploding 10 kilotons of TNT, roughly equivalent to the atomic bomb dropped on Hiroshima in 1945. Think about that comparison carefully. The bomb that killed approximately 80,000 people instantly and devastated an entire city released the same energy required to accelerate a single kilogram to interstellar speeds. 1 kilogram. The mass of a small laptop computer. A bag of sugar. A liter of water. Sending that trivial mass to the stars requires nuclear weapon levels of energy. Now scale this to realistic spacecraft masses. The smallest interstellar probe, capable of carrying useful scientific instruments and a communication system, might weigh 100 kilograms. Accelerating it to 10% light speed requires energy equivalent to 1,000 Hiroshima bombs, the entire nuclear arsenal of a major world power, detonated simultaneously, might barely suffice to launch a minimal robotic probe toward a nearby star. A crude spacecraft capable of sustaining human life for the decades required to reach even our nearest stellar neighbor would weigh hundreds of thousands of kilograms at minimum. Current estimates suggest that a self-sustaining vessel carrying even a small crew would mass millions of kilograms when you account for life support systems, radiation shielding, living quarters, food production facilities, medical equipment, and all the redundant systems needed for a journey where no rescue is possible. The energy requirements for such a vessel climb into ranges that make humanity's nuclear arsenals look trivial. We are talking about energy levels that exceed the total output of human civilization over centuries. We are approaching energy requirements that rival the output of the sun itself over meaningful time periods. Chemical rockets cannot provide these energies. This statement requires emphasis because chemical rockets have carried every spacecraft humanity has ever launched. Every satellite orbiting Earth, every probe exploring the solar system, every astronaut who has left our atmosphere. All of them rode chemical rockets into space, yet chemical rockets are fundamentally incapable of interstellar travel. The most powerful rocket ever built was the Saturn V that launched Apollo astronauts to the Moon. This engineering marvel stood 363 feet tall and weighed 6.5 million pounds fully fueled. Its 5 F1 engines produced 7.6 million pounds of thrust at liftoff, generating 160 million horsepower. The sound of a Saturn V launch could be heard from 100 miles away and cause seismographs to register readings across the state of Florida. This staggering output could accelerate the Apollo spacecraft to roughly 40,000 kilometers per hour, enough to escape Earth's gravity and reach the Moon in 3 days. But this velocity represents only 0.004% of the speed needed for interstellar travel. The most powerful rocket ever built achieved less than 1/25,000th of interstellar velocity. Building larger chemical rockets does not solve the problem. The rocket equation ensures that additional fuel adds more mass, requiring more fuel to accelerate, creating diminishing returns that rapidly approach zero. This mathematical trap has haunted rocket engineers since Konstantin Tsiolkovsky first derived the equation in 1897. The rocket equation states that the velocity change a rocket can achieve depends on its exhaust velocity and the ratio between its initial mass and final mass. The relationship is logarithmic, meaning that doubling your fuel does not double your velocity. To double velocity change, you must square the mass ratio. To triple velocity, you must cube it. For chemical rockets with exhaust velocities around 4.5 kilometers per second, reaching 10% of light speed would require a mass ratio so enormous that the number overflows any practical calculation. The fuel required would exceed the mass of the observable universe. This is not an exaggeration. This is the mathematical consequence of the rocket equation applied to chemical propulsion. A chemical rocket designed for interstellar travel would need to be so massive that no amount of fuel could lift it from Earth's surface. The rocket would collapse under its own weight before ignition. Even if you somehow assembled such a rocket in space, the fuel requirements would exceed the mass of all matter within billions of light years. Chemical rockets are simply the wrong tool for interstellar travel. The problem lies in chemistry itself. The energy stored in chemical bonds is determined by electromagnetic interactions between electrons in atoms. When hydrogen and oxygen combine to form water in a rocket engine, the energy released comes from the rearrangement of electrons into lower energy configurations. This energy is real and substantial, enough to lift massive payloads into orbit. But it is fundamentally limited by the strength of chemical bonds. No arrangement of atoms can store more energy per kilogram than the best existing rocket fuels. You cannot make a chemical bond stronger than physics allows. You cannot extract more energy from combustion than chemistry permits. The ceiling is absolute and insurmountable. Every chemical rocket that will ever be built, regardless of how advanced the engineering becomes, will be limited to exhaust velocities of roughly 5 kilometers per second. This is approximately 1/60,000th of light speed. Nuclear propulsion offers improvements over chemical rockets, but faces its own limitations. Nuclear thermal rockets heat propellant using a fission reactor instead of chemical combustion. The reactor can achieve temperatures far higher than any chemical reaction, accelerating propellant to exhaust velocities roughly twice those of chemical rockets. This doubles efficiency but still falls billions of times short of interstellar requirements. NASA developed nuclear thermal rocket technology during the NERVA program in the 1960s and 70s. These engines worked. They were tested repeatedly in the Nevada desert, demonstrating that nuclear reactors could indeed propel spacecraft more efficiently than chemical rockets. The program was cancelled for political and budgetary reasons, not technical failure. But even if NERVA-style engines were developed to their full potential, they could not enable interstellar travel. Doubling exhaust velocity improves the rocket equation significantly for travel within our solar system. Missions to Mars become more practical. Journeys to the outer planets become faster. But doubling exhaust velocity does essentially nothing against the 25 trillion miles separating us from Proxima Centauri. Project Orion proposed a far more radical approach to nuclear propulsion. Conceived in the 1950s by physicist Freeman Dyson and others, Orion imagined spacecraft propelled by exploding nuclear bombs behind a massive pusher plate. Each explosion would vaporize a layer of the pusher plate, creating a plasma that would push against the remaining plate and accelerate the spacecraft. The concept sounds insane, but the physics actually works. Nuclear explosions release enormous energy in very short time frames. By directing this energy against a pusher plate, you can achieve accelerations far beyond what any conventional rocket provides. Calculations suggested that an Orion spacecraft could achieve 3 to 5% of light speed, fast enough to reach Proxima Centauri in roughly 100 to 150 years. The technical challenges of nuclear pulse propulsion proved immense, even for this relatively modest performance. Each explosion would stress the pusher plate with forces exceeding millions of pounds. The plate would need to absorb repeated nuclear blasts without cracking, warping, or melting through. Thousands of nuclear bombs would need to detonate in precisely controlled sequences, each positioned perfectly relative to the plate, each triggering at exactly the right moment. Radiation shielding would add enormous mass to protect crew members from the nuclear inferno propelling their vessel. The spacecraft would need to carry its entire bomb supply from the start, meaning thousands of nuclear weapons would need to be launched into space and assembled into a single vessel. Every aspect of the concept presented engineering nightmares that made the Apollo program look simple by comparison. Political and environmental concerns eventually killed Project Orion. The Limited Test Ban Treaty of 1963 prohibited nuclear explosions in space, effectively outlawing Orion-style propulsion. Environmental groups raised alarms about the prospect of launching thousands of nuclear weapons through Earth's atmosphere, where a launch failure could scatter radioactive material across continents. But even if these concerns were somehow addressed, Project Orion promised century-long voyages requiring thousands of nuclear weapons per mission. The fastest conceivable Orion spacecraft would still require longer than a human lifetime to reach Proxima Centauri. Crews would be born, grow old, and die during the journey. Multiple generations would pass before arrival. Ion drives represent the current state-of-the-art for high-efficiency propulsion. These elegant engines accelerate ions using electric fields rather than chemical combustion or nuclear reactions. Ionized gas particles are expelled at exhaust velocities 10 times higher than chemical rockets, dramatically improving the rocket equation for long-duration missions. The Dawn spacecraft used ion propulsion to explore the asteroid belt between 2011 and 2018. Its ion engines operated for over 50,000 hours, demonstrating remarkable reliability for deep space missions. Several commercial satellites use ion thrusters for station keeping, making small adjustments to their orbits over years of operation. But ion drives produce minuscule thrust levels, measured in millinewtons rather than the millions of newtons produced by chemical rockets. Accelerating a spacecraft with ion propulsion resembles trying to push a car by breathing on it. The acceleration is real and measurable but imperceptibly small. NASA's Dawn spacecraft accelerated by roughly 7 meters per second per day when its ion engines were operating. This means that after a full day of continuous thrust, the spacecraft was moving about 25 kilometers per hour faster than before. At this rate, reaching 10% of light speed would require approximately 12,000 years of continuous acceleration. 12,000 years ago, the last ice age was ending. Humans had not yet invented agriculture. Mammoths still roamed the Earth. The entire span of human civilization would pass during the acceleration phase alone, before the spacecraft even began its decades-long coast toward another star. Ion drives excel at gradually building velocity over long periods within our solar system. They cannot provide the sustained high thrust needed for practical interstellar travel. Solar sails harvest pressure from sunlight itself, using photons bouncing off reflective surfaces to generate thrust. This elegant concept requires no fuel whatsoever, potentially enabling indefinite acceleration as long as sunlight remains available. The spacecraft carries nothing but a large reflective surface, and photons from the sun push against this surface like wind pushing against a sailing ship. The physics of solar sailing is well understood and has been demonstrated in practice. The Japanese Icarus probe demonstrated solar sailing in 2010, successfully using a 14-meter sail to adjust its trajectory during a mission to Venus. The Planetary Society's LightSail 2 spacecraft demonstrated controlled solar sailing in Earth orbit in 2019. But solar radiation pressure decreases with the square of distance from the Sun. At Earth's orbit, solar radiation pressure is approximately 9 micronewtons per square meter. At Mars orbit, this drops to roughly 4 micronewtons per square meter. By the time a spacecraft reaches Jupiter's orbit, solar pressure has fallen to roughly 4% of its value near Earth. At Saturn's orbit, it has dropped to 1%. At interstellar distances, the Sun provides essentially zero propulsive force. The same inverse square law that governs light intensity ensures that solar sails become useless long before a spacecraft exits our solar system. Solar sails might accelerate spacecraft to impressive velocities within the inner solar system, but they cannot push anything across the void between stars. Laser sails address this limitation by using powerful lasers instead of sunlight. A laser array on Earth or in orbit could beam concentrated energy toward a departing spacecraft, maintaining propulsive force across vastly greater distances than sunlight allows. The laser could track the receding spacecraft and continue pushing it long after the Sun's radiation pressure becomes negligible. The Breakthrough Starshot initiative proposes exactly this approach. Founded in 2016 with funding from billionaire Yuri Milner, the project envisions a 100-gigawatt laser array that would accelerate gram-scale probes to 20% of light speed. At this velocity, the tiny spacecraft could reach Proxima Centauri in approximately 20 years. The physics actually works for tiny payloads. A laser sail measuring 4 meters across, weighing only grams, with a spacecraft payload measured in grams rather than kilograms, could potentially be accelerated to interstellar velocities by a sufficiently powerful laser. The acceleration would occur over mere minutes, with the tiny sail experiencing thousands of g-forces that would instantly kill any human occupant. This represents humanity's most realistic near-term path to interstellar space. Within decades, if sufficient funding and engineering effort were devoted to the project, humanity could potentially launch the first probes toward other stars. These probes would be smaller than your thumbnail, carrying cameras and communication equipment weighing less than a paperclip. They would have no ability to slow down upon arrival, merely flashing past their target star at 20% of light speed, while frantically photographing whatever they could observe. The catch is devastating for human aspirations. Only microscopic probes can be accelerated this way. The same physics that enables tiny sails prohibits larger payloads. The thrust imparted by a laser depends on the power of the laser and the reflectivity of the sail. The acceleration achieved depends on this thrust divided by the mass being accelerated. Double the mass and you halve the acceleration. A probe weighing 2 grams instead of 1 gram would accelerate half as fast and require twice the laser power to achieve the same velocity. A probe weighing 1 kilogram, still far too small to carry a human being, would require 1,000 times more laser power than Breakthrough Starshot proposes. Scaling laser propulsion to human-carrying spacecraft requires laser arrays producing millions of times more power than Breakthrough Starshot envisions. A laser capable of accelerating a crewed spacecraft to interstellar speeds would need to output energy comparable to the total power consumption of human civilization. As of 2023, global power consumption averages approximately 18 terawatts. Accelerating a crewed spacecraft would require sustained laser output, exceeding this figure by factors of thousands. Building such a laser remains far beyond any technology we can envision. Powering it continuously for the months or years of acceleration needed would require energy resources exceeding anything humanity currently possesses. The laser array would need to remain precisely aimed at a receding spacecraft across distances measured in astronomical units, maintaining beam coherence over millions of miles. And this analysis assumes that someone solves the problem of slowing down. A laser sail can only be pushed, not pulled. The laser array remains in our solar system, pointing outward. When the spacecraft arrives at its destination, there is no laser to slow it down. Either the interstellar travelers flash past their target at a significant fraction of light speed, unable to stop and explore, or some other technology must be developed for deceleration. Antimatter propulsion represents the theoretical pinnacle of rocket technology. When matter meets antimatter, both annihilate completely, converting their entire mass into energy according to Einstein's famous equation, E = mc squared. The energy released equals the mass destroyed multiplied by the speed of light squared. This mass-energy equivalence means that antimatter is the most energy-dense fuel physically possible. Antimatter is approximately 1,000 times more energy-dense than nuclear fission, which itself is roughly 1,000,000 times more energy-dense than chemical fuels. 1 gram of antimatter annihilating with 1 gram of normal matter releases approximately 43 kilotons of TNT equivalent energy, nearly 3 times the Hiroshima bomb yield. A perfect antimatter rocket could theoretically achieve velocities approaching light speed. The exhaust velocity of a matter-antimatter annihilation rocket approaches light speed itself, dramatically improving the rocket equation compared to any other known propulsion technology. An antimatter rocket could conceivably accelerate a spacecraft to 50 or 60% of light speed, using fuel masses comparable to the payload mass. The practical obstacles are so staggering that antimatter propulsion remains firmly in the realm of science fiction. Humanity currently produces approximately 10 nanograms of antimatter per year, mostly as a byproduct of particle physics experiments at facilities like CERN. This production is incidental, created when high-energy particle collisions generate matter-antimatter pairs as a side effect. 10 nanograms per year. 100 million years of production at current rates would accumulate 1 gram of antimatter. The journey to Proxima Centauri would require kilograms of antimatter at minimum. More likely, hundreds of kilograms for a crewed mission. Current production rates would need to increase by factors of billions to generate useful quantities within meaningful timeframes. The energy cost of producing antimatter presents an even more fundamental problem. Creating antimatter requires concentrating energy to such extreme levels that particle-antiparticle pairs spontaneously appear from the vacuum. The energy input required to create antimatter vastly exceeds the energy obtained by annihilating it. Current production efficiency is approximately 1 part in 10 billion, meaning that for every 10 billion joules of energy invested in antimatter production, only 1 joule worth of antimatter results. This makes antimatter fundamentally impractical as a fuel source. By basic thermodynamics, you cannot create energy from nothing. The energy that would be released by annihilating antimatter must first be invested to create that antimatter. With efficiency ratios of 1 in 10 billion, antimatter production is an energy sink, not an energy source. Storage presents equally impossible challenges. Antimatter annihilates instantly upon contact with normal matter. A single antiproton touching a single proton results in complete annihilation of both particles, releasing gamma radiation and other high-energy products. Containing antimatter requires preventing any contact whatsoever with normal matter. Current antimatter traps use powerful magnetic fields to suspend charged antiparticles in perfect vacuum. These traps work for individual antiprotons or positrons, holding them in isolation from normal matter for periods measured in minutes or hours. The ALPHA experiment at CERN has trapped antihydrogen atoms for over 16 hours. A remarkable achievement of physics, but utterly inadequate for spacecraft propulsion. Storing the grams or kilograms needed for interstellar propulsion remains beyond any known technology. The magnetic fields required to contain macroscopic quantities of antimatter would themselves require enormous energy and equipment mass. A container failure at any point during the journey would result in immediate annihilation, releasing energy equivalent to nuclear weapons inside the spacecraft. Even if production and storage challenges were somehow solved through physics breakthroughs we cannot currently envision, antimatter rockets face the same tyranny of the rocket equation that limits all propulsion systems. The mathematics improves dramatically compared to chemical or nuclear rockets, but the fundamental exponential relationship between velocity and fuel mass remains. An antimatter rocket, traveling at 50% of light speed, would need to carry antimatter fuel, massing more than the payload itself. At 70% of light speed, fuel requirements triple. At 80%, fuel mass exceeds payload by factors of 10. Reaching 90% of light speed requires fuel masses dozens of times greater than the payload being accelerated. The same diminishing returns that doom chemical rockets eventually doom antimatter rockets as well. The threshold simply occurs at higher velocities. Chemical rockets hit the wall at a few percent of light speed. Antimatter rockets hit the wall at perhaps 70 or 80% of light speed, but the wall exists for all rocket-based propulsion systems regardless of fuel type. Some physicists have proposed even more exotic propulsion concepts that attempt to circumvent the rocket equation entirely. The Alcubierre drive, proposed by Mexican physicist Miguel Alcubierre in 1994, warps spacetime itself rather than accelerating a spacecraft through space. The concept creates a bubble of warped spacetime that moves faster than light, while the spacecraft inside remains stationary relative to local space. This sounds like obvious science fiction, yet the mathematics within general relativity permit such solutions. Einstein's equations describe how mass and energy curve spacetime. The Alcubierre metric describes a configuration where space contracts in front of a bubble and expands behind it, carrying the bubble and anything inside it faster than light relative to distant observers. The concept does not violate special relativity because the spacecraft never actually moves through space faster than light. Instead, space itself moves, carrying the spacecraft along like a surfer riding a wave. The surfer can travel faster than they could swim because the wave itself is moving. However, the mathematics of the Alcubierre drive require negative energy density to create the necessary spacetime curvature. Normal matter and energy produce positive curvature. The warp bubble requires regions of negative curvature, achievable only through exotic matter with negative energy density. Negative energy density may not exist in our universe at macroscopic scales. Quantum mechanics predicts that certain vacuum states can exhibit temporarily negative energy densities, but these effects occur at scales far too small to exploit for propulsion. No experiment has ever detected macroscopic negative energy, and no theory convincingly explains how to produce it. Original calculations suggested that creating a warp bubble would require negative energy, equivalent to the mass of Jupiter, converted entirely into exotic matter. Later revisions to the mathematics by physicists like Harold White reduced the energy requirement substantially, potentially to masses equivalent to several hundred kilograms. But even these optimistic revisions require exotic matter we have no idea how to produce, in quantities we have no idea how to accumulate, configured in geometries we have no idea how to achieve. The Alcubierre drive remains an interesting mathematical curiosity with no connection to engineering reality. Wormholes offer another theoretical shortcut through space-time. Rather than traveling the full distance between stars through normal space, a spacecraft could enter a wormhole, traverse a short tunnel through higher dimensional space-time, and emerge at its destination. Einstein's equations permit wormhole solutions. The mathematics of general relativity describes how space-time could be curved to create such tunnels. However, all known wormhole solutions in physics are either traversable but require exotic matter with negative energy density, or naturally occurring but non-traversable. Natural wormholes, if they exist, collapse so rapidly that nothing can pass through them before they pinch shut. Keeping a wormhole open long enough for passage requires threading it with exotic matter that exerts negative pressure, physically holding the throat open against its natural tendency to collapse. No experiment has ever detected exotic matter with negative energy density. No theory convincingly explains how to produce it. No observation has ever found evidence that wormholes exist naturally anywhere in the universe. The existence of traversable wormholes remains purely speculative, interesting mathematical solutions to Einstein's equations, with no demonstrated connection to physical reality we can access or exploit. The tyranny of physics reveals itself most clearly when you attempt comprehensive energy calculations for interstellar travel. Accelerating a modest spacecraft weighing 100,000 kilograms to 10% of light speed requires approximately 4.5 times 10 to the 21st joules of energy. Written out, this is 4.5 sextillion joules. For comparison, total human civilization energy consumption in 2023 was approximately 5.8 times 10 to the 20th joules. Accelerating a single modest spacecraft to interstellar speeds requires roughly 8 times the total annual energy consumption of every human being on Earth combined. This energy would need to be not merely generated but efficiently converted into spacecraft, kinetic energy. A process that inevitably involves substantial losses. Accelerating a spacecraft large enough to sustain human life for decades, with all necessary life support, radiation shielding, living space, food production, medical facilities, and redundant systems, would require energy outputs that stagger calculation. Such a vessel might mass millions of kilograms. The energy required would exceed human civilization's total energy production over centuries. These are not engineering problems awaiting clever solutions. They are not challenges that more funding or better technology will overcome. They are fundamental physical constraints arising from the laws of nature themselves. Energy cannot be created from nothing. Mass energy equivalence determines how much propulsive force any fuel can provide. The rocket equation governs how fuel requirements scale with desired velocity. These laws apply everywhere in the universe. They apply to every civilization that might attempt interstellar travel, regardless of their technological sophistication or the duration of their scientific development. A species that has been spacefaring for 1 million years still faces the same physics we face. Their rockets still obey the Tsiolkovsky equation. Their kinetic energy requirements still scale with velocity squared. This universality has profound implications for the search for extraterrestrial intelligence and for understanding our place in the cosmos. If the physics truly prohibits practical interstellar travel, then every civilization, no matter how ancient or advanced, faces the same barriers we face. The universe might be filled with intelligent species, each gazing at the same stars we see, each calculating the same depressing numbers we calculate, each trapped within their own stellar neighborhood by the same inexorable physics. Civilizations, separated by a few light years, might as well be separated by infinity. Communication might be possible through radio signals traveling at light speed, but physical visitation might be forever beyond reach. The stars appear close in our night sky. Their light reaches us easily, carrying information about their composition, their planets, their potential for harboring life. We can analyze stellar spectra from our telescopes. We can detect planets orbiting distant suns. We can measure atmospheric compositions of worlds we will never visit. Information travels freely across the cosmos at light speed. But light is massless. It requires no energy to accelerate to light speed because it travels at light speed by its very nature. Spacecraft are massive. Every kilogram requires enormous energy to accelerate. This fundamental asymmetry between information and transportation may define the ultimate limits of exploration for all intelligent life everywhere in the cosmos. We can know about the universe. We may never be able to explore it. The physics that permits us to see the stars is the same physics that prevents us from reaching them. Imagine surviving the engineering challenges. Imagine developing propulsion technology capable of accelerating a spacecraft to 10 or 20% of light speed. Imagine solving the energy requirements through some breakthrough in physics we cannot currently envision. Imagine building the laser arrays or antimatter factories, or nuclear pulse engines that could push a vessel across the void between stars. Even then, even after solving every engineering problem that currently seems insurmountable, the human body itself becomes the final obstacle. Space is trying to kill you. This is not metaphor or exaggeration. Every moment beyond Earth's protective atmosphere, your body endures assault from radiation, vacuum, temperature extremes, microgravity, and the absence of environmental conditions your biology requires for survival. Within our solar system, these hazards can be managed through careful engineering and limited exposure times. Astronauts spend months on the International Space Station and return to Earth with measurable but manageable health impacts. Missions to Mars lasting 2 to 3 years appear feasible with sufficient shielding and medical support. Interstellar space amplifies every danger to levels that may be fundamentally incompatible with human survival. The journey times stretch from months to decades. The distances eliminate any possibility of rescue or resupply. The radiation environment exceeds anything humans have ever experienced. The isolation surpasses any psychological challenge our species has faced. The human body evolved for one specific environment over billions of years. That environment exists nowhere else in the known universe. Cosmic radiation represents the most insidious and unavoidable threat to interstellar travelers. On Earth's surface, we live beneath a protective cocoon that shields us from the universe's violence. Our planet's magnetic field extends thousands of miles into space, deflecting charged particles streaming from the sun and from beyond our solar system. Our atmosphere absorbs and scatters the particles that penetrate this magnetic shield. By the time cosmic radiation reaches the ground, it has been reduced to a tiny fraction of its intensity in open space. We evolved under this protection. Our DNA repair mechanisms developed to handle background radiation levels found on Earth's surface, not the bombardment that exists beyond our magnetic shield. Every cell in your body contains molecular machinery designed to fix radiation damage, but this machinery has limits. Exceed those limits and damage accumulates faster than repair can occur. Beyond Earth's magnetosphere, astronauts receive radiation doses hundreds of times higher than average ground levels. The International Space Station orbits within the outer edges of Earth's magnetic protection, roughly 250 miles above the surface. Even this partial shielding leaves crews exposed to radiation levels that significantly increase cancer risk over 6-month missions. Astronaut Scott Kelly, who spent nearly a year aboard the station, returned with measurable genetic changes including altered gene expression and chromosomal abnormalities. Interstellar space offers no protection whatsoever. Once a spacecraft leaves the heliosphere, the bubble of solar wind that surrounds our solar system, it enters a radiation environment that would kill unprotected humans within days. Galactic cosmic rays permeate every cubic meter of interstellar space, composed of protons and heavier atomic nuclei, accelerated to velocities approaching light speed by the most violent events in the universe. These particles originate from supernova explosions, where dying stars detonate with the energy of billions of nuclear weapons. They stream from the accretion disks of black holes, where matter spirals inward at relativistic speeds. They emerge from the jets of active galactic nuclei, powered by supermassive black holes consuming entire stars. The universe is a violent place, and that violence manifests as high-energy particles streaming through every region of space. Galactic cosmic rays travel with energies millions of times greater than anything produced in particle accelerators on Earth. The Large Hadron Collider, the most powerful accelerator ever built, accelerates protons to energies of roughly 7 trillion electron volts. Cosmic rays routinely carry energies of 100 trillion electron volts. Some individual particles have been detected with energies exceeding 100 billion electron volts, more energy in a single subatomic particle than a professionally pitched baseball. When these particles strike human tissue, they do not merely pass through like light through glass. They interact violently with the atoms in your body, shattering molecular bonds and creating cascades of secondary radiation. A single heavy cosmic ray nucleus passing through a human brain can kill thousands of neurons along its track, leaving a microscopic trail of destruction through neural tissue. The damage is not limited to immediate cell death. Cosmic rays shatter DNA molecules, breaking the double helix that carries genetic information. Your cells contain repair mechanisms that can fix some DNA damage, but high-energy particles create complex breaks that are difficult or impossible to repair correctly. Misrepaired DNA leads to mutations. Accumulated mutations lead to cancer. Over the decades required for interstellar travel, cumulative radiation exposure would increase cancer risk to near certainty. Scientists have calculated the radiation dose an unshielded human would receive during a journey to Proxima Centauri at 10% of light speed. The 40-year voyage would expose travelers to approximately 4,000 millisieverts of radiation, roughly 1,000 times the annual dose received by people living on Earth's surface. This level of exposure causes acute radiation syndrome, hair loss, nausea, bleeding, organ failure, death. No amount of passive shielding can completely block high-energy cosmic rays. Particles with energies exceeding 100 billion electron volts penetrate meters of solid metal. Water provides better protection than metal because it contains hydrogen atoms that can absorb neutrons. But effective water shielding would require layers measured in meters rather than centimeters. Scientists have calculated minimum shielding requirements for interstellar crews. Effective protection would require surrounding habitation areas with approximately 5 meters of water or equivalent hydrogen-rich material. The mass of this shielding for a modest habitation module would exceed thousands of tons. For a spacecraft large enough to support a crew for decades, shielding mass could reach tens of thousands of tons. Remember the tyranny of the rocket equation. Every kilogram added to spacecraft mass requires exponentially more fuel to accelerate. Adding tens of thousands of tons of radiation shielding would multiply already impossible energy requirements by additional orders of magnitude. The shielding needed to protect human bodies makes human bodies effectively untransportable at interstellar velocities. Active shielding using powerful magnetic fields has been proposed as an alternative to mass shielding. Superconducting magnets generating fields millions of times stronger than Earth's magnetic field could theoretically deflect charged particles around a spacecraft, creating an artificial magnetosphere similar to the natural one protecting Earth. The engineering challenges are enormous. Generating magnetic fields strong enough to deflect galactic cosmic rays requires superconducting coils operating at temperatures near absolute zero. These coils would need to be enormous, potentially kilometers in diameter, to create a protective bubble large enough for a spacecraft. The power requirements would add substantial mass to the vessel. The magnetic field itself might pose health risks to crews living within it for decades, as strong magnetic fields can interfere with neural function and cardiac rhythms. Even the most optimistic assessments of magnetic shielding conclude that it could reduce but not eliminate cosmic ray exposure. High-energy particles would still penetrate any achievable magnetic field. Crews would still accumulate radiation damage over decades of travel. Cancer rates would still be elevated compared to Earth populations. The technology might make interstellar travel survivable rather than immediately lethal, but it would not make it safe. Beyond the acute damage from cosmic rays, interstellar travelers would face chronic radiation effects that accumulate over years and decades. The lens of the human eye is particularly sensitive to radiation damage. Cataracts develop when radiation disrupts the proteins that keep the lens transparent. Astronauts who have spent extended time in space show elevated rates of cataract formation. Interstellar travelers would likely develop vision impairment during their voyage, potentially becoming blind before reaching their destination. The cardiovascular system also suffers from radiation exposure. Studies of atomic bomb survivors and radiation therapy patients show elevated rates of heart disease following significant radiation doses. The mechanism involves damage to the cells lining blood vessels, leading to inflammation and accelerated atherosclerosis. Interstellar travelers might survive cancer, only to die of heart attacks caused by radiation damage to their circulatory systems. The immune system degrades under radiation stress. White blood cells that fight infection are among the most radiation-sensitive cells in the body. Prolonged exposure suppresses immune function, leaving the body vulnerable to infections that healthy immune systems would easily defeat. A spacecraft traveling for decades would become an incubator for opportunistic infections as crew immune systems progressively failed. Neurological damage may prove the most insidious long-term effect. Animal studies show that radiation exposure causes cognitive impairment, memory loss, and behavioral changes. Mice exposed to radiation equivalent to cosmic ray doses show reduced performance on learning tasks and increased anxiety. Human brains are not fundamentally different from mouse brains in their sensitivity to radiation. Interstellar travelers might arrive at their destination with dementia, their minds degraded by decades of particle bombardment. The psychological challenges of interstellar travel may prove as insurmountable as the physical hazards. Humans are social creatures. We evolved in communities of perhaps 150 individuals, surrounded by familiar landscapes, embedded in networks of relationships extending across generations. Our mental health depends on connection, communication, and the presence of others who share our experiences and validate our perceptions. A spacecraft traveling to Proxima Centauri would experience communication delays that make real-time conversation with Earth impossible. At 10% of light speed, the spacecraft would require roughly 40 years to reach its destination. During the journey, the vessel would recede from Earth at enormous velocity, with the distance increasing every moment. Communication signals travel at light speed regardless of spacecraft velocity. When the vessel is 1 light-year from Earth, messages take 1 year to travel in each direction. A crew member sending a birthday greeting to a child on Earth would wait 2 years for a reply. By the time that reply arrived, the child would be 2 years older than when the message was sent. As the journey progresses, delays compound. At the halfway point, roughly 2 light-years from Earth, messages require 4 years for a round trip. A crew member learning of a parent's illness would wait years to discover whether the parent survived or died. By the time news arrived, the events would be ancient history, the people involved aged or deceased, the circumstances completely changed. At the destination, 4.2 light-years from Earth, communication delays reach 8.5 years. A message sent upon arrival at Proxima Centauri would not receive a response until nearly a decade later. The people who sent the original message might be dead by the time replies arrived. Conversations would span generations. The crew would be communicating with ghosts, receiving messages from a past that no longer exists, sending messages to a future they would never see. This temporal dislocation would create psychological effects unlike anything humans have experienced. Every communication with Earth would be a reminder of separation, a connection that emphasizes distance rather than bridging it. The crew would know that everyone they left behind was aging and dying while they traveled, that the Earth they departed no longer existed by the time they arrived anywhere. Studies of isolated human populations provide sobering insights into the psychological costs of separation. Antarctic research stations, particularly during the winter months when evacuation becomes impossible, report increased rates of depression, anxiety, interpersonal conflict, and cognitive impairment. Crews describe the winter over syndrome characterized by irritability, memory problems, sleep disturbances, and a fugue state called the Antarctic stare. Submarine crews confined to vessels for weeks or months show similar effects. The combination of confinement, limited social contact, lack of natural light, and awareness of danger creates psychological stress that accumulates over time. Minor irritations become major grievances. Mental health deteriorates, even among individuals selected for psychological resilience. Astronauts aboard the International Space Station experience psychological challenges despite constant communication with Earth, regular resupply missions, and the psychological comfort of orbiting their home planet. They can see Earth through every window, a constant reminder that home is only hours away in an emergency. Despite these advantages, astronauts report elevated stress, sleep disturbances, and interpersonal tensions during 6-month missions. Now imagine decades of travel through absolute emptiness. Imagine looking out a window and seeing nothing but unchanging stars, the same view day after day, month after month, year after year, decade after decade. Imagine being unable to see Earth, unable to receive timely communication from loved ones, unable to return regardless of any emergency. Imagine knowing that the people you left behind are aging and dying while you hurtle through the void, that relationships are ending, children are being born and growing old, civilizations are rising and falling, all while you drift through unchanging darkness. The psychological effects of multi-decade isolation in a confined space with no possibility of rescue or return remain completely unknown because no human has ever experienced anything remotely comparable. The longest isolation experiments have lasted months or at most a few years. The psychological demands of interstellar travel would exceed these experiments by factors of 10 or more. Generation ships propose circumventing voyage duration by launching populations that would live and die aboard spacecraft, with descendants eventually arriving at distant stars. Parents would board the vessel knowing they would never see the destination. Their children would be born in transit, live their entire lives aboard the ship, and die before arrival. Grandchildren or great-grandchildren would finally complete the journey begun by ancestors they never knew. This concept appears frequently in science fiction, where generation ships cross interstellar distances over centuries while internal societies evolve in isolation from Earth. The stories often focus on social dynamics, conflicts between generations, and the challenge of maintaining mission purpose across spans of time that exceed historical memory. The biological requirements for generation ships present challenges that science fiction often ignores. A self-sustaining population requires minimum genetic diversity to avoid inbreeding depression over multiple generations. When individuals within a population share too many genes, recessive genetic disorders become common and overall fitness declines. Small populations, isolated for many generations, eventually suffer increased rates of birth defects, reduced fertility, and general health decline. Scientists estimate that a minimum viable population for long-term genetic health requires at least 160 individuals carefully selected for genetic diversity. Some calculations suggest that thousands of individuals would be needed to maintain healthy genetic variation over the centuries required for interstellar travel. The crew would not be a handful of astronauts, but a small city launched into the void, Supporting populations of this size for centuries demands closed-loop life support systems, recycling all water, atmosphere, and nutrients with near-perfect efficiency. Nothing can be wasted. Nothing can be replenished from external sources. Every molecule of oxygen breathed out must be converted back to breathable oxygen. Every drop of water excreted must be purified and returned to drinking supplies. Every scrap of food waste must be composted and used to grow new food. No technology exists for closed-loop life support operating indefinitely. The International Space Station recycles some water and oxygen, but requires regular resupply missions delivering food, spare parts, and replacement consumables. The station could not survive for years without external support, let alone centuries. The biosphere. Two experiments in the early 1990s attempted to create a sealed ecosystem, supporting 8 humans for 2 years. This ambitious project constructed a 3-acre enclosed facility in Arizona, containing multiple biomes, including rainforest, ocean, and agricultural areas. The goal was demonstrating that humans could survive indefinitely within a closed system, a necessary precursor to space colonization. The project encountered cascading failures that required outside intervention. Oxygen levels dropped dangerously, as concrete in the structure absorbed carbon dioxide faster than plants could replace oxygen. Food production fell short of requirements, forcing crew members to enter a near-starvation diet. Pest species multiplied while pollinators died off, disrupting agricultural cycles. Social conflicts among crew members intensified as conditions deteriorated. Biosphere. 2 demonstrated that creating a stable, closed ecosystem is far more difficult than anyone anticipated. Natural ecosystems achieve stability through billions of years of evolution, developing feedback mechanisms and redundancies that human engineers cannot replicate. Artificial ecosystems are fragile, prone to cascading failures where one disruption triggers others in unpredictable chains. Scaling such systems to support hundreds or thousands of people for centuries introduces failure modes we cannot anticipate. What happens when a disease sweeps through the only species capable of pollinating food crops? What happens when equipment essential for water recycling fails and cannot be repaired? What happens when social conflicts escalate to violence among populations that cannot escape each other? Generation ships also face profound ethical questions that deserve serious consideration. Crew members born during the voyage never chose to participate in the mission. They would be born into confinement, live their entire lives within the vessel, and die without ever experiencing the freedom that their ancestors knew. Their fates would be determined by decisions made by people who died before they were born. Every generation would sacrifice their existence for descendants they would never meet. Parents would raise children knowing those children would never see Earth, never walk under an open sky, never experience anything beyond the ship's walls. The entire purpose of their lives would be serving a mission launched by ancestors and completed by descendants, with their generation serving merely as a bridge between past and future. The philosophical implications of condemning future generations to this existence have never been adequately addressed. Do we have the right to create human beings whose entire lives will be spent in service to goals they did not choose? Is it ethical to bring children into existence knowing they will never experience freedom or autonomy? These questions have no easy answers, and the generation ship concept forces us to confront them directly. Hibernation, or suspended animation, offers a theoretical alternative to generation ships. If humans could be safely put into stasis for decades and revived at the destination, voyage duration becomes irrelevant to crew survival. Travelers would experience the journey as a single extended sleep, closing their eyes at departure and opening them at arrival with no subjective time passing between. This concept is equally popular in science fiction, where crew members enter cryogenic pods and emerge decades or centuries later, unaged and ready to explore new worlds. The reality of suspended animation is far more complicated than fiction suggests. Cryopreservation, freezing bodies at extremely low temperatures, causes lethal damage to tissues through multiple mechanisms. As cells cool, water within them forms ice crystals. These crystals are jagged structures that puncture cell membranes, destroying the boundaries that keep cellular content separated from the external environment. Thawing does not repair this damage. The cells remain dead, their contents leaking through ruptured membranes. Some organisms have evolved natural antifreeze compounds that prevent ice crystal formation. Certain frogs, insects, and fish can survive being frozen solid because their tissues contain proteins and sugars that interfere with ice crystallization. These organisms enter a state of suspended animation during winter and revive when temperatures rise. Scaling this protection to human physiology has proven impossible. Human bodies contain trillions of cells, organized into complex tissues and organs. Distributing antifreeze compounds evenly throughout this volume, ensuring that every cell receives protection before freezing, presents challenges that no one has solved. Organs can be cryopreserved individually with some success, but whole body preservation invariably causes fatal damage. Vitrification offers an alternative approach. By cooling tissues extremely rapidly, water can be converted directly to a glass-like solid without forming ice crystals. This process has successfully preserved individual organs, including kidneys that have been vitrified, stored, rewarmed, and transplanted into animals where they functioned normally. Scaling vitrification to whole human bodies faces the same distribution challenges as cryoprotectants. Cooling must occur rapidly and uniformly throughout the body, which requires somehow removing heat from the core faster than it naturally dissipates. Large bodies cool slowly. The exterior freezes while the interior remains warm, creating temperature gradients that stress tissues and cause damage. Even if suspended animation were achieved through some future technology, revival after decades of stasis introduces additional unknowns. Metabolism cannot be completely halted without death. Even at temperatures near absolute zero, chemical reactions occur slowly. Over decades, these reactions accumulate, potentially causing damage that would not occur over shorter periods. Cellular repair mechanisms would need to function perfectly upon revival to restore tissues to health. These mechanisms themselves might be damaged by the preservation process. A person revived after decades of stasis might wake with accumulated damage that their body cannot repair, aging decades in subjective moments. Medical emergencies during interstellar voyages present nightmarish scenarios, regardless of whether crews travel awake or in hibernation. A crew member experiencing appendicitis, a condition easily treated on Earth, would face life-threatening danger in interstellar space. The spacecraft would need to carry surgical facilities, trained surgeons, anesthesia equipment, and all supplies needed for the procedure. A simple surgery that takes an hour on Earth becomes a desperate struggle for survival when the nearest hospital is light years away. Heart attacks, strokes, cancers, and traumatic injuries would be equally challenging. Modern medicine assumes access to civilization's resources. When someone collapses on a city street, an ambulance arrives within minutes carrying trained paramedics and equipment for emergency care. Hospitals provide intensive care units, surgical theatres, diagnostic imaging, and specialist physicians available around the clock. An interstellar spacecraft would need to carry equipment and expertise for every conceivable medical emergency, while remaining limited by mass constraints that prohibit comprehensive medical capabilities. Hard choices would be required. Which imaging equipment to include? Which surgical specialties to train crew members in? Which medications to carry? Knowing that supplies are limited and some conditions will be untreatable. A surgical emergency occurring years from Earth would require the crew to perform procedures they may have trained for but never practiced. Surgeons on Earth develop expertise through thousands of operations under supervision before working independently. Spacecraft crew would need to develop this expertise through simulation alone, then perform real surgery for the first time when a colleague's life depends on their skill. Medications expire. The chemical compounds in pharmaceutical drugs degrade over time, losing potency and potentially becoming toxic. Missions lasting decades would need to carry medications that remain effective far longer than current formulations, or include facilities for manufacturing pharmaceuticals during the voyage. Equipment fails, surgical instruments dull, diagnostic devices malfunction, electronic components degrade under radiation exposure. Maintaining medical capabilities across decades would require spare parts for every device, tools for repair, and expertise to diagnose and fix failures. Infections develop resistance to limited antibiotic supplies. Bacteria evolve rapidly, developing resistance to antibiotics they are exposed to frequently. A spacecraft with limited antibiotic diversity would create selection pressure for resistant strains. Eventually, all available antibiotics might become ineffective against bacteria that have evolved in the ship's environment. Every medical textbook ever written assumes access to civilization's resources. Interstellar crews would face medical challenges utterly unlike anything in human experience, combining the dangers of wilderness medicine with the impossibility of evacuation and the duration of decades rather than days. Equipment failure presents related challenges beyond medical systems. Every mechanical system eventually wears out or breaks down. Moving parts wear against each other. Seals degrade and leak. Electronic components fail. Structural materials fatigue under repeated stress. A spacecraft traveling for decades would experience failures that engineers cannot predict. Modern spacecraft rely on mission control for troubleshooting and repair guidance. When something fails aboard the International Space Station, teams of engineers on Earth analyze telemetry, diagnose problems, and develop repair procedures. Astronauts receive step-by-step instructions and can consult with experts in real time when complications arise. Communication delays of years or decades eliminate this support entirely. A crew facing equipment failure would need to diagnose and repair the problem using only the resources aboard and their own expertise. They could send a message to Earth describing the failure, but the response would not arrive for years. By then, the crew might be dead, or might have solved the problem independently, or might have developed new problems that render the original question irrelevant. A spacecraft would need to carry spare parts for every component that might fail, along with the tools and expertise to perform repairs. Complex systems like computer networks, power generation, and life support contain thousands of components, each representing a potential point of failure. Carrying spares for everything would add enormous mass. Failing to carry a critical spare could doom the mission. The Voyager probes illustrate equipment longevity challenges in interstellar space. After nearly 50 years of operation, Voyager 1 has experienced multiple instrument failures. Its plasma science instrument stopped working in 2007. Its ultraviolet spectrometer failed in 2016. Systems that functioned perfectly at launch have degraded over decades of operation. Voyager's power output decreases approximately 4 watts per year as its plutonium fuel decays. The generators that convert nuclear decay to electricity have degraded beyond their design specifications. Engineers have progressively shut down instruments to conserve power for the most essential functions. By 2030, insufficient power will remain to operate any instruments. The probe will continue drifting through interstellar space as dead metal. Its mission ended not by dramatic failure, but by the inevitable decay of materials and energy sources. Human interstellar missions would need to sustain far more complex systems for similar or longer durations. Life support, propulsion, navigation, communication, power generation, thermal control, radiation shielding, and hundreds of subsidiary systems would all need to function continuously for decades. A single irreparable failure in any critical system could doom the entire mission. Consider the failure modes. Power generation fails and life support systems shut down. Navigation sensors fail and the spacecraft drifts off course with no way to correct. Communication systems fail and the crew loses all contact with Earth. Hull integrity fails and atmosphere leaks into space. Any of these failures, occurring at any point during a decades-long voyage, would be fatal with no possibility of rescue. The fragility of human flesh and the hostility of space create barriers that technology alone cannot overcome. We evolved to survive on Earth's surface, sheltered by atmosphere, protected by magnetic field, sustained by ecosystems that took billions of years to develop. Every aspect of human biology assumes the presence of environmental conditions that exist nowhere else in the known universe. Our bones require gravity to maintain density. In microgravity, astronauts lose roughly 1% of bone mass per month. Over decades, this loss would render skeletons too fragile to support body weight under any gravity. Our cardiovascular systems require gravity to function properly. In microgravity, blood pools in the upper body, causing facial swelling and increased intracranial pressure. Long-term effects include vision, impairment, and potential brain damage. Our muscles atrophy without resistance to work against. Astronauts on the International Space Station exercise 2 hours daily to minimize muscle loss and still return to Earth significantly weakened. Our immune systems depend on environmental exposures to develop and maintain proper function. Sealed environments lead to immune dysfunction and increased vulnerability to disease. Interstellar space represents the ultimate hostile environment. Temperatures near absolute zero that would freeze human tissue solid in seconds. Radiation that penetrates all practical shielding and damages every cell it touches. Vacuum that would cause human blood to boil and lungs to rupture. Distances so vast that no help could ever arrive from Earth. The human body is simply not designed to survive in this realm. We are creatures of Earth, evolved for Earth, dependent on Earth's conditions for every biological function. Adapting human bodies to survive interstellar travel might require changes so fundamental that the resulting beings would no longer be human in any meaningful sense. Perhaps the flesh itself is the ultimate barrier, more insurmountable than the physics of propulsion or the vastness of cosmic distance. Perhaps biology, not engineering, defines the limit of human reach into the cosmos. The accumulated evidence points toward a disturbing conclusion. Interstellar travel may be permanently impossible for biological entities. The distances are too vast, the energy requirements too extreme, the hazards too numerous, the human body too fragile. Every proposed solution introduces new obstacles that may prove equally insurmountable. We have acknowledged the fragility of flesh that limits human survival. This is not a problem awaiting solution. This is not a challenge that more funding or better technology will overcome. This is a fundamental constraint arising from the nature of reality itself. The laws of physics that govern our universe conspire to prevent biological creatures from crossing the void between stars. These laws apply everywhere, to every civilization that might attempt interstellar travel, regardless of how advanced their technology becomes or how long they have been trying. This realization transforms how we understand humanity's place in the cosmos. We are not a species temporarily confined to one planet, while we develop the technology to spread among the stars. We are not early explorers waiting for better ships. We are not pioneers delayed by engineering challenges that will eventually be solved. We may be permanently isolated within our solar system, able to see countless worlds but unable to reach any of them. The psychological impact of this understanding deserves acknowledgement. For generations, humanity has assumed that interstellar travel was merely a matter of time. Science fiction conditioned us to expect faster-than-light drives as an inevitable technology. We internalized the assumption that advanced civilizations naturally become spacefaring, that reaching the stars was humanity's destiny. This assumption was never based on physics. It was based on narrative convenience and human optimism. Writers needed ways to get characters from star to star, so they invented technologies that physics does not permit. Audiences wanted to imagine humanity among the stars, so storytellers obliged with tales of galactic empires and interstellar federations. The gap between fiction and reality widened with each new franchise, until we forgot that gap existed. Accepting permanent stellar isolation requires abandoning assumptions we did not know we held. It requires grieving a future we believed was ours. It requires reconceptualizing humanity's cosmic role in ways that may feel like defeat. The stars we gazed upon as destinations become decorations, illuminating our imprisonment rather than our possibilities. But this grief, while valid, may be premature. What we lose in possible destinations, we gain in understanding. What we sacrifice in dreams of galactic empire, we recover in clearer vision of achievable futures. Accepting limits is not the same as accepting failure. It is the beginning of wisdom about what remains possible. The universe becomes a prison of infinite beauty. 2 trillion galaxies fill the observable cosmos, each containing billions of stars, many harboring planetary systems where life might flourish under alien suns. We have detected thousands of exoplanets orbiting distant stars. We have identified worlds in habitable zones where liquid water could exist. We have measured atmospheric compositions, suggesting conditions compatible with life as we understand it. We can detect these worlds. We can analyze their atmospheres. We can speculate about the civilizations that might inhabit them. We can photograph their stars and calculate their orbital parameters and estimate their surface temperatures. We can know them in extraordinary detail across light years of separation, but we cannot visit them. The light that brings us information about distant stars cannot be matched by physical journeys to reach them. Photons travel freely at the cosmic speed limit, carrying data about stellar compositions and planetary atmospheres across any distance. Mass cannot match this freedom. Every kilogram we wish to send requires energy proportional to velocity squared, creating barriers that scale toward infinity as speeds approach light. This asymmetry between information and transportation defines the boundaries of cosmic exploration. We can learn about the universe without limit. Our knowledge can expand indefinitely as telescopes grow more powerful and detection methods grow more sensitive. But our physical presence remains confined to one small corner of existence, a single solar system among billions in a single galaxy among trillions. This cosmic isolation has profound implications for understanding the apparent absence of extraterrestrial visitors. The Fermi paradox, named for physicist Enrico Fermi, who reportedly asked "Where is everybody?" during a lunch conversation in 1950, asks why we have never detected evidence of alien civilizations given the billions of years the galaxy has existed and the billions of stars it contains. The mathematics of the paradox seem straightforward. The Milky Way contains between 200 billion and 400 billion stars. The galaxy formed approximately 13 billion years ago. If even a tiny fraction of stars host planets capable of supporting life, and even a tiny fraction of those planets develop intelligent civilizations, and even a tiny fraction of those civilizations survive long enough to become spacefaring, the galaxy should be teeming with alien activity. Conservative calculations suggest that a civilization with technology only modestly superior to our own could colonize the entire galaxy in roughly 1 million years, using spacecraft traveling at a fraction of light speed. This sounds like an enormous time span until you realize it represents less than 1% of the galaxy's age. Even if intelligent life is rare, emerging only once per million years somewhere in the galaxy, thousands of civilizations should have had time to spread everywhere by now. Yet we see no evidence of alien presence. No spacecraft have visited our solar system that we can detect. No structures have been observed around other stars that suggest engineering. No radio signals have been received that carry signs of artificial origin. No probes have drifted into our neighborhood carrying messages from distant civilizations. The galaxy appears empty, despite calculations suggesting it should be full. Countless proposed solutions to the Fermi paradox involve alien behaviors or circumstances that prevent them from reaching Earth or making themselves known. Perhaps civilizations inevitably destroy themselves through nuclear war or environmental collapse before achieving interstellar capability. Perhaps advanced species transcend physical existence and lose interest in exploration. Perhaps aliens have visited, but we fail to recognize them. Perhaps they are deliberately avoiding contact for reasons we cannot comprehend. But perhaps the simplest explanation is that interstellar travel is universally impossible. Every civilization, no matter how ancient or advanced, faces the same physics we face. The speed of light is constant throughout the universe, unchanged since the first moments after the Big Bang. The rocket equation applies everywhere, to alien spacecraft as surely as to human ones. Energy requirements scale identically, regardless of who is doing the calculating. The void between stars is equally hostile to all biological life, regardless of the biochemistry involved. If interstellar travel is impossible for everyone, then the Fermi paradox dissolves. The galaxy might be filled with intelligent species, each trapped within their own stellar neighborhood, each gazing at the same stars we observe, each wondering if they are alone. The cosmic silence results not from the absence of civilizations, but from the impossibility of contact across distances requiring centuries or millennia to bridge. Imagine a galaxy teeming with life. Millions of civilizations orbiting millions of stars, each developing unique cultures and technologies and philosophies. They build telescopes and detect each other's planets. They listen for radio signals and occasionally detect hints of artificial origin. They know, with scientific certainty, that they are not alone in the universe, but they can never meet. The distances between them exceed what any technology can cross. Light-speed communication requires generations for a single exchange. Physical travel requires time spans exceeding the duration of species. Each civilization exists in permanent isolation, aware of cosmic neighbors, but unable to reach them, like prisoners in separate cells who can hear each other's voices but never touch. This interpretation transforms the Great Filter concept in astrobiology. The Great Filter is a hypothetical barrier that prevents intelligent life from becoming widespread in the universe. Researchers have proposed various candidates for the filter, various catastrophes or limitations that might prevent civilizations from spreading among the stars. Perhaps the filter lies in our past. Perhaps the origin of life is extraordinarily improbable, and Earth was lucky enough to pass through this barrier billions of years ago. Perhaps the evolution of complex multicellular life is extremely rare, a bottleneck that most planets with simple life never traverse. Perhaps the development of intelligence requires such specific conditions that it almost never occurs. If the filter lies behind us, we may be among the rare survivors, perhaps the only civilization in the galaxy to have emerged. Perhaps the filter lies in our future. Perhaps technological civilizations inevitably destroy themselves through nuclear war, ecological collapse, or artificial intelligence run amok. Perhaps every species that develops the power to destroy itself eventually does so. Perhaps we are approaching a gauntlet that has killed every civilization before us. If the filter lies ahead, we face existential dangers we may not survive. But perhaps the filter is neither behind us nor ahead of us. Perhaps the filter is the void itself. Not a catastrophe that destroys civilizations, but a barrier that no technology can overcome. Not a danger that kills species, but a limitation that confines them. The interstellar distances themselves might be the great filter, preventing any civilization from spreading beyond its stellar neighborhood, regardless of how long it survives or how advanced it becomes. This interpretation offers both comfort and despair. Comfort, because it suggests humanity is not facing an impending catastrophe that has killed all who came before us. The filter is not something we must pass through. It is something we are already experiencing, a condition of existence rather than a challenge to survive. We are not destined for destruction. We are destined for isolation. Despair because it suggests we will never encounter alien civilizations, no matter how long we search or how advanced we become. The cosmic loneliness is permanent. The silence will never be broken by contact. We can know that others exist without ever being able to reach them. Consider the implications for the search for extraterrestrial intelligence. SETI programs have scanned the skies for decades, searching for radio signals that might indicate technological civilizations. Billions of dollars have been spent on telescopes and signal processing equipment designed to detect artificial transmissions from distant stars. If interstellar travel is impossible, aliens cannot visit Earth, but they can still potentially communicate. Electromagnetic signals travel at light speed across any distance, limited only by the power of transmitters and the sensitivity of receivers. A sufficiently powerful radio signal could be detected across the entire galaxy. An alien civilization that wanted to announce its presence could build a transmitter powerful enough to reach any star within tens of thousands of light years. But communication faces its own temporal barriers. The speed of light is fast by human standards but slow by cosmic ones. A signal sent to the center of our galaxy requires 26,000 years to arrive. A response takes another 26,000 years to return. Round-trip communication with the galactic center requires 52,000 years. No human civilization has lasted 52,000 years. Recorded history spans only about 5,000 years. The longest-lived human cultures have persisted for perhaps 10,000 years before transforming into something fundamentally different. Meaningful dialogue across galactic distances requires timescales exceeding the duration of any civilization in human history. What message could remain relevant across 50,000 years? What question could a civilization ask? Knowing the answer would not arrive until their descendants had evolved into something unrecognizable. What information could you transmit, knowing the recipient would not exist for millennia? Communication with nearby stars faces shorter but still substantial delays. A message sent to Proxima Centauri requires 4 years and 3 months to arrive. A response takes another 4 years and 3 months to return. Round-trip communication with our nearest stellar neighbor requires 8.5 years. This is within human experience. You could send a message and live to receive a reply, but the delay transforms communication into something barely recognizable. You could not have a conversation. You could not ask a question and clarify misunderstandings in the response. You could send a single message and receive a single reply, then repeat this process perhaps a dozen times across a human lifetime. Stars farther away impose proportionally longer delays. A message to Sirius requires 17 years for round-trip communication. A message to Vega requires 50 years. A message to the nearest star known to host Earth-like planets in another system might require decades or centuries for a single exchange. The search for extraterrestrial intelligence might better focus on detecting artifacts rather than signals. A civilization unable to cross interstellar space might still launch robotic probes carrying durable messages. These probes, traveling for millennia at achievable velocities, might eventually drift through other stellar systems. They would not carry living beings. They would carry information, recorded greetings from civilizations that might no longer exist. Finding such an artifact would transform human understanding. It would prove that other intelligent species exist, that consciousness arose independently elsewhere in the universe, that we are not alone even if we are isolated. The artifact itself might carry information about its creators, their biology, their culture, their technology, their hopes for whoever might find their message. But receiving such an artifact would also confirm our isolation. The probe would have traveled for thousands or millions of years to reach us. Its creators would be long dead, their civilization transformed beyond recognition or extinct entirely. We could learn that others existed without ever being able to meet them. The artifact would be a gravestone, marking the presence of something that lived and died among distant stars. Our solar system becomes infinitely more precious when viewed as our permanent home, not a launching pad for journeys among the stars, but a destination in itself, the only destination we will ever have. 8 planets, hundreds of moons, millions of asteroids, and billions of comets offer resources and environments that could potentially support human civilization indefinitely. Earth will not remain habitable forever. In approximately 1 billion years, the Sun's increasing luminosity will push surface temperatures beyond what liquid water can withstand. Long before that, in perhaps 500 million years, increasing solar radiation will cause the oceans to evaporate and the atmosphere to escape into space. Earth has a finite future as a living world, but 1 billion years is an almost inconceivable span of time. Human civilization has existed for roughly 10,000 years. The entire evolution of complex multicellular life on Earth required only about 600 million years. The time remaining before Earth becomes uninhabitable exceeds the duration of complex life by a factor of almost 2. Within this time span, humanity could expand throughout the solar system, building civilizations on worlds that currently lie barren and silent. Mars could be terraformed over centuries or millennia, its thin atmosphere thickened with greenhouse gases, its frozen water melted into seas, its rust-red surface gradually greened with engineered life. The process would require technologies we do not yet possess, and timescales exceeding any human project ever attempted. The asteroid belt contains mineral wealth exceeding Earth's entire crust. Millions of rocky bodies orbit between Mars and Jupiter, remnants of a planet that never formed, available for mining, processing, and construction. The materials exist to build millions of space habitats, each housing thousands or millions of people in environments tailored to human needs. Jupiter's moons harbour subsurface oceans that might already contain life. Europa, Ganymede, and Callisto each possess more water than all of Earth's oceans combined, kept liquid by tidal heating beneath icy crusts. These worlds could support human outposts, scientific stations studying alien biochemistries, or refuges for species seeking environments different from Earth's. Saturn's moon Titan offers a unique environment with liquid hydrocarbon lakes beneath a thick nitrogen atmosphere. The outer planets and their moons provide resources and locations for civilizations adapted to cold and darkness. Even Pluto and the Kuiper Belt objects might someday host human presence. Outposts at the edge of our solar system, gazing outward toward stars we can never reach. The energy output of the Sun could power civilizations vastly more advanced than our current societies. Our star produces approximately 400 trillion watts of power, radiating in all directions into space. Earth intercepts only about 1/billionth of this output. The rest radiates away unused, energy squandered into the void. A Dyson swarm, a concept proposed by physicist Freeman Dyson in 1960, describes a collection of solar collectors surrounding the Sun to capture a significant fraction of its energy output. Not a solid sphere, which would be structurally impossible, but a swarm of millions or billions of individual collectors, each orbiting independently, together intercepting most of the Sun's radiation. Such a structure could capture energy sufficient to support trillions of humans living throughout the solar system. Power requirements that seem astronomical by current standards would become trivial. Energy-intensive projects that seem impossible today, like terraforming planets or accelerating probes to interstellar velocities, would become achievable through the abundance of captured solar power. Space habitats constructed from asteroid materials could provide living space exceeding Earth's total surface area by factors of millions. The physicist Gerard K. O'Neill proposed designs for such habitats in the 1970s, rotating cylinders that provide artificial gravity through centrifugal force. Millions of people could live inside each cylinder, in environments designed from scratch for human habitation. Earth has approximately 500 million square kilometers of surface area, most of it ocean or uninhabitable terrain. The useful land area available for human civilization is perhaps 150 million square kilometers. The asteroid belt contains enough material to construct habitats with total interior surface area exceeding billions of square kilometers. Even using only a fraction of available materials, humanity could build living space thousands of times greater than Earth provides. This vision of solar system civilization represents humanity's realistic long-term future. not spreading among the stars as science fiction promised, but expanding throughout our own stellar neighborhood, building societies in environments ranging from Mercury's sun-baked surface to the frozen darkness of the outer planets and beyond. Each world offers unique challenges and opportunities. Each could become home to distinct human cultures adapted to local conditions. Mercury, closest to the Sun, receives intense radiation and experiences extreme temperature variations. Settlements would need to shelter in permanently shadowed craters near the poles, or migrate continuously around the planet, staying within the twilight zone between burning day and freezing night. The challenges are immense, but not impossible. Venus, shrouded in clouds of sulfuric acid with surface temperatures hot enough to melt lead. Humans could not walk on the Venusian surface, but they might float above it in habitats suspended by buoyant gases. Mars remains the most Earth-like world in the solar system, with a 24-hour day, polar ice caps, and evidence of ancient water flows. Terraforming Mars would require centuries but could eventually create a second Earth. A world where humans could walk on the surface without pressure suits, where rain falls from Martian skies and rivers flow through Martian valleys. The moons of Jupiter and Saturn offer environments stranger than any on Earth. Europa's subsurface ocean might host life evolved independently of any terrestrial ancestor. Titan's methane lakes create landscapes unlike anything in human experience. Enceladus sprays geysers of water ice into space, evidence of geological activity that could power settlements for millennia. The outer solar system, from Uranus and Neptune to the Kuiper Belt and Oort cloud, offers cold, dark environments far from the sun's warmth. Settlements there would depend entirely on nuclear power or other energy sources independent of solar radiation. They would exist in isolation more profound than anywhere else humans might live. Outposts at the edge of our stellar neighborhood. Each of these environments would shape the humans who lived there. Martian colonists would adapt to lower gravity and longer days. Asteroid dwellers would develop cultures suited to microgravity and enclosed spaces. Deep space inhabitants would evolve traditions appropriate for isolation and self-reliance. Over millennia, humanity might diversify into multiple species, each adapted to its particular environment, descendants of Earth spreading across the solar system, even if they can never spread beyond it. The psychological adjustment required to accept this future is substantial. We have grown up with stories of galactic civilization as humanity's destiny. We have internalized assumptions about interstellar travel that physics does not support. Accepting permanent stellar isolation requires abandoning these assumptions and reconceptualizing what human success in the cosmos might mean. Perhaps there is something noble in this limitation. A species that cannot spread infinitely must learn to live sustainably within its stellar neighborhood. Resources remain finite even across the solar system. The asteroid belt contains vast wealth, but not infinite wealth. The sun produces enormous energy, but not unlimited energy. Cooperation becomes essential when nowhere else exists to flee conflicts. Long-term thinking replaces the frontier mentality of infinite expansion. Human history has been shaped by the availability of frontiers. When populations faced resource constraints, when conflicts escalated beyond resolution, when societies became oppressive, those who could move away did so. The Americas offered escape from European constraints. The American West offered escape from Eastern crowding. The promise of new frontiers has always provided relief valves for social pressure. A solar system, civilization without access to other stars, would lack this relief valve. Conflicts could not be resolved by one party leaving for distant territories. Resources could not be supplemented by colonizing new systems. This constraint might force human societies to develop cooperation and sustainability that frontier access has allowed us to avoid. The beautiful tragedy of cosmic consciousness becomes acute when viewed from this perspective. Evolution produced beings capable of understanding the universe's vastness while simultaneously being unable to explore it. We developed telescopes that revealed billions of galaxies while being trapped within one stellar system. We decoded the physics governing cosmic distances while discovering those same physics forever bar our passage. Some might find this depressing. The universe revealed as an infinite museum where we can look but never touch. Countless worlds visible in our instruments, each potentially harboring wonders beyond imagination, all permanently beyond reach. The stars reduced from destinations to decorations, illuminating our imprisonment rather than our possibilities. Others might find this liberating. If the stars are unreachable, then Earth and the solar system become our entire reality. Every resource needed for human flourishing exists within our stellar neighborhood. Every challenge facing humanity can be addressed within our accessible cosmos. The pressure to develop impossible technologies evaporates, replaced by focus on achievable goals. The anxiety of failing to reach the stars dissolves when reaching them was never possible. The universe's hostility to interstellar travel might also protect developing civilizations from external threats. Science fiction frequently imagines alien invasions, advanced species crossing interstellar distances to conquer or consume primitive worlds like Earth. These scenarios assume that interstellar travel is possible for sufficiently advanced civilizations, that technology can overcome the barriers we have discussed. If interstellar travel is impossible for everyone, then alien invasion is impossible too. Isolation works both ways. The same barrier that prevents human expansion also prevents alien interference. Each stellar system becomes an isolated preserve, where life can develop without interference from beyond. No civilization, however advanced or malevolent, can reach us across the void. This protection extends across cosmic time. The sun will continue shining for approximately 5 billion years before exhausting its hydrogen fuel and expanding into a red giant. Human civilization has existed for roughly 10,000 years. Even if we cannot leave our solar system, the time available for development exceeds our current existence by a factor of 500 million. Within this time span, human descendants could become beings as different from us as we are from bacteria. Evolution operates on timescales of millions of years. Cultural evolution operates faster. Technological evolution faster still. Given billions of years of development, confined within one solar system, what might humanity become? We cannot imagine it. Our cognitive limits prevent us from conceiving transformations so vast, but we can recognize that the time span available dwarfs any human experience. Civilizations could rise and fall thousands of times. Species could evolve and be replaced by successors. Intelligence itself might transform into something we would not recognize as thought. All of this could happen while the sun still burns, while the solar system still provides the energy and resources needed for development. The philosophical implications of permanent isolation deserve deeper exploration. Evolution favored brains capable of modeling the environment, predicting consequences, and planning future actions. These capabilities proved useful for survival on the African savanna, where our ancestors evolved, but consciousness exceeded what survival required. We developed the ability to contemplate cosmic scales that have no relevance to finding food or avoiding predators. We became capable of understanding the universe's size and age, its structure and evolution, its laws and possibilities. This capacity seems gratuitous, an evolutionary accident that produced capabilities far beyond what our survival demanded. Evolution produced beings who could imagine reaching the stars, even though stars are unreachable. Natural selection favored curiosity and exploration that served well for discovering new hunting grounds or water sources. These same drives now point toward destinations that physics forbids. We are creatures with interstellar ambitions confined to interplanetary reality. Why would evolution produce such beings? Why would natural selection favor capacities that cannot be fulfilled? Perhaps the answer lies in the difference between what evolution selects for and what evolution produces. Evolution does not design organisms for specific purposes. It simply favors traits that enhance reproductive success. In particular environments, our cosmic curiosity may be a side effect of cognitive capabilities that evolved for entirely different reasons. Or perhaps consciousness serves a purpose beyond individual survival. Perhaps consciousness is the universe's way of knowing itself, even if conscious beings cannot travel through it. Through telescopes and mathematics, through physics and astronomy, through thought experiments and computer simulations, we explore the cosmos without physically traversing it. Our minds travel where our bodies cannot go. Every distant galaxy we photograph becomes accessible through information, even if unreachable through transportation. We cannot visit Andromeda, but we can measure its size and composition, its velocity and rotation, its star formation rate and supermassive black hole. We know Andromeda in scientific detail that would have seemed miraculous to observers even a century ago. Every planet we detect through transit observations reveals itself through data, even if we can never walk on its surface. We cannot visit Proxima Centauri b, but we can estimate its mass and orbital period, speculate about its atmosphere and surface conditions, calculate whether it might harbor liquid water. The world becomes known to us through instruments, even as it remains physically inaccessible. Every star whose spectrum we analyze gives up its secrets, even if we can never approach its burning face. The light that reaches us carries information about stellar composition, temperature, age, and evolution. We read the universe like a book, turning pages made of photons, comprehending contents we cannot touch. The distinction between information and transportation might define the boundaries of cosmic exploration. Information travels freely across the universe, limited only by the speed of light. Photons carry data from the edge of the observable universe to our instruments, revealing conditions 14 billion years in the past across 14 billion light-years of space. Transportation requires energy proportional to mass, creating barriers that may be fundamentally insurmountable. Intelligent beings might expand their knowledge without limit, while remaining confined to tiny regions of physical space. This is our condition. This is perhaps the condition of every intelligent species in the universe. Cosmic consciousness distributed across billions of stellar neighborhoods, each learning about the others through light that travels freely while mass remains trapped. This realization points toward futures involving exploration through intelligence rather than presence. If biological beings cannot survive interstellar travel, artificial minds operating aboard tiny spacecraft might traverse distances that biological creatures cannot. Machines do not suffer from cosmic radiation as acutely as living tissue. Machines do not experience psychological isolation. Machines do not require food or water or oxygen. Machines can be built small enough for laser propulsion to practical velocities. The Breakthrough Starshot initiative imagines exactly this scenario. Gram-scale probes accelerated to 20% of light speed by laser arrays could reach Proxima Centauri in approximately 20 years. These probes would be smaller than postage stamps, carrying cameras and communication equipment miniaturized to nearly molecular scales. They would have no ability to slow down upon arrival, merely flashing past their target at tremendous velocity while photographing whatever they could observe. Upon arrival, they could photograph any planets, analyze atmospheric compositions through spectroscopy, and transmit findings home using laser communication. This data would require 4 years to reach Earth, but would arrive within a human lifetime of launch. A person who witnessed the launch could live to see images of planets orbiting another star. Such probes could not establish colonies or enable human visits. They represent pure information gathering, expanding our knowledge without expanding our physical presence. They would confirm or refute our models of planetary formation. They would reveal whether Proxima Centauri b has an atmosphere, oceans, or signs of biological activity. They would transform our understanding of what exists in our cosmic neighborhood. A fleet of such probes could eventually survey every star within a few dozen light years, revealing what exists nearby without enabling us to travel there. We would know our neighborhood in intimate detail while remaining confined to one stellar system within it. The universe would become progressively more known and progressively more inaccessible. This information-focused exploration might satisfy our deepest drives without requiring impossible technologies. The fundamental human need is not to physically stand on alien worlds, but to know what exists on them. Curiosity drives us more than the desire for physical presence. If robotic emissaries can provide knowledge, the core purpose of exploration is achieved even without human presence. Looking up at the night sky, we see light that has traveled for years, centuries, or millennia to reach our eyes. Each photon carries information about its source, encoded in wavelength and arrival time. The universe communicates with us through this light, revealing its contents across distances we cannot physically cross. Perhaps this is enough. Perhaps consciousness exists not to colonize the cosmos, but to comprehend it. Perhaps the purpose of intelligent life is not to spread, but to understand. Perhaps we were never meant to walk among the stars, only to know them from afar. The stars burn in their courses, separated by voids that may forever exceed our capacity to cross. Each night they appear overhead, constant and unreachable, beautiful and forbidden. We can calculate their distances with precision measured in decimal places. We can analyze their compositions atom by atom through spectroscopy. We can detect their planets and speculate about their inhabitants. We can know them with scientific intimacy while remaining strangers who will never meet. But we cannot visit them. The prison of light holds us close while showing us everything we cannot touch. The universe grants us eyes to see infinity while binding our bodies to one small corner of existence. Humanity's future lies within our solar system. Expanding across these 8 planets and their countless moons, harvesting the sun's energy for civilizations beyond current imagination, building societies among the asteroids and comets that trace endless orbits around our star, finding meaning and purpose within our stellar neighborhood, because no other neighborhoods will ever be accessible. This is not failure. This is acceptance. This is wisdom about the nature of reality and our place within it. The universe made us capable of seeing infinity while restricting us to one small corner of existence. We are island species on an island world in an island solar system, surrounded by an ocean of emptiness that cannot be crossed. The stars are lighthouses marking shores we can never reach, yet we persist. We continue looking upward. We keep building telescopes and launching probes and dreaming of distant worlds. Perhaps this striving defines consciousness more than any destination could. Perhaps the meaning lies in the reaching, not the arrival. Perhaps what matters is not where we can go, but what we can understand. The true scale of interstellar travel is not measured in light years or parsecs. It is measured in impossibility. The distances are real. The physics is confirmed. The barriers are fundamental. They arise from the nature of space and time and energy, from laws that govern every particle in the universe, from mathematics that applies equally to every civilization that might ever attempt the journey. And understanding all of this changes nothing about our need to gaze upward and wonder what exists among those unreachable points of light. The knowledge of impossibility does not diminish the beauty. The certainty of confinement does not eliminate the wonder. We remain creatures who evolve to explore, even when exploration means only looking and never touching. We are alone in our solar system. We may always be alone in our solar system. Other intelligences may exist around other stars, equally isolated, equally wandering, equally unable to reach us as we are to reach them. The universe extends infinitely in all directions, filled with wonders we can observe but never visit. This is our reality. This is our home. This is our permanent address in an infinite cosmos. The stars continue burning. The void continues separating. And we continue dreaming of journeys we may never take, across distances we may never cross. The tyranny of physics holds us prisoner, while the beauty of the universe holds us captive. Both conditions may persist forever. Twin aspects of existence that define what it means to be conscious in a cosmos that permits awareness but prevents travel. Perhaps this is the true meaning of cosmic consciousness. Not to conquer the universe, but to witness it. Not to spread among the stars, but to understand them. Not to escape our stellar neighborhood, but to accept it as our eternal home while never ceasing to wonder what lies beyond. The night sky reveals everything and permits nothing. We can see it all. We can reach almost none of it, and somehow, knowing this, we continue looking up. Perhaps that persistence, that refusal to stop wondering despite the impossibility of arriving, defines what consciousness truly means. Perhaps the meaning of intelligent life is not found in destinations reached, but in questions asked. Not in territory conquered, but in mysteries contemplated. We are the universe knowing itself, confined to one small perspective but capable of comprehending the whole. That may be enough. That may be everything. That may be the only purpose consciousness was ever meant to serve.